scatter plots and correlation. So it's when we talk about bivariate data, we're collecting two pieces of information about something and we plot it to see if there is some relationship between these two things. And that's the graph, the scatter plot. Here, this is actual data that I pulled from, I can't remember what year it was, Year 11 yearly exams. The relationship between what a student scored in their maths exam, so the 2-unit one, and their extension one, and there were all the results. There's the scatter. Then I did the same for English and English extension. There was the scatter. Then I thought, well, why not look at maths extension versus English extension? We get a different scatter. Then I said, well, how about maths extension and business studies? And finally I said, well, what about maths extension and PDHPE? Now, the correlation is the strength of that scatter, and it moves between -1 and 1. 1 would be a perfect scatter. That would be a nice linear one. There's this direct relationship. Yep, not a problem. -1 also has a direct relationship, but in a bad way. It would have the line would be going in a negative direction, have a negative slope. And 0, I guess, would be no correlation at all. It's just no. That first one actually has a correlation of 0.81, a very strong correlation, and you would hope that would be true. It makes sense. English was only 0.49. Kind of makes sense when you think about the courses. See, maths, the maths course and the maths extension course really is one thing. We're just building on it. It's all the one. Whereas, as you know, in English, they're actually two separate courses. Whilst you'd like to see some sort of correlation there, there's no reason why it had to be a strong one. I mean, that one we would call moderate. Maths extension versus English extension, 0.23, we're now starting to get a weak correlation. 0.1, that one actually has a correlation of 0.01, so virtually no correlation between maths extension and business studies, and the final one there actually has negative 0.15, so another weak one, but in the negative direction. With any graph, we put the independent variable on the horizontal axis and the dependent variable on the vertical axis, and that's no difference with a scatter plot. However, when we're talking about bivariate data, it's not really obvious which one's the independent and which one's the dependent. In that case, it probably doesn't matter which axis you put the information on. What we're going to be looking at is pretty much linear correlation. So we're looking for these lines. But it is possible for a non-linear correlation. So if the scatter came out something like that, we could see, okay, it looks like there's an exponential relationship between the two. And that would be quite strong. That one there would be, probably looks like the hyperbola. So some sort of inverse correlation. Y equals 1 on x was probably the equation. And I guess theoretically, you could have something like that. I just made those numbers up. They weren't actually test results. Because, I mean, wow, that's insane, some of these. But you could have something like that, and it would be a quadratic correlation. So we're interested in linear correlation. And that's where lines of best fit come in. Because the reality is, when we do our experiments and what have you, for them to line up perfectly would be very unusual. So we get our line of best fit to try and get what that relationship is. In order to draw lines of best fits, then you really need to identify multiple points, because you might have two pieces of information that have exactly the same data. And so when you plot it, it looks like you've only drawn one point there. How do you identify it? Well, sometimes you just write the number on top of it. So it happened here 3 times, so it happened 4 times. Or a different shape, maybe I'll put a triangle instead of a dot. So that way when you're drawing your line of best fit, you know, oh, that point actually, there's several of those there, maybe I need to come closer to that point. So right, back to our maths versus maths extension. I'll draw my line of best fit in, do it by eye. There you go, I put that in there. So using that line then, I can make some predictions about how people went. So for example, if someone scored 0 in the maths extension task, they probably scored 50% in advance. Well, that doesn't really make sense, but that's what my line of best fit. And that brings up the difference between interpolation, which is when I predict results within the range. And so for something like this, that seems a reasonable thing to do. If I've got a set of data and I'm going to make predictions within that set of data, okay, someone scoring 60% in maths extension probably got a result of around 80%. That's a reasonable thing to do. And extrapolation. And you have to be very careful when you extrapolate data. The example I've got there is 20%. Someone who got 20% would have got 60%. Maybe not, but certainly that 0 one I talked about before probably doesn't make sense. So extrapolation when it's outside my data set that I've collected, interpolation when it's within what I collected. But there's this other thing called causation. And when I said to you before that one of the most misunderstood things about correlation, what it actually is, correlation and causation. Look at these. Just because you have a correlation doesn't necessarily mean that it's true, that relationship is true. During summer, people get hay fever. There also is a lot of pollen in the air in summer. In fact, there is a strong correlation between the presence of pollen and hay fever. So I will draw the conclusion that pollen causes hay fever. Now, that one actually is a sensible correlation. There have been lots of studies to prove that is indeed the case. But that's the point. When you find a strong correlation, all you're really doing is finding something that, hey, maybe this is worth investigating further. It looks like there's a relationship. So maybe we'll now go and do more studies to see if indeed there is. We don't just look at the correlation and go, oh, there you go, proven. Because look at this one. During summer, the sale of ice cream increases, but so does death by drowning. Well, there's a strong correlation between ice cream sales and death by drowning. Well, therefore, I'm going to draw the conclusion that ice cream causes drowning. The more ice cream you eat, the more likely you are to drown. Clearly, that's absurd, okay? That is not a sensible correlation. It's just two things that happen more in summer. But that's what I mean. If you came up with that, someone probably could get a wonderful research grant and got given a lot of money to go, oh, well, let's investigate this further. I know they get research grants for all sorts of things. And go and investigate it. So the correlation actually is identifying things that, hey, maybe this is something worth investigating further. So it doesn't mean that this is actually the cause of it. Correlation does not mean causation. 15D. There's a little chat on correlation.